Okay, we are proving this identity. This variable is phi. If you don't like phi, in fact, I'm going to change it to x. This is a strategy that you can do. Just change it all to x. And then I draw the line down the middle. If you do change variables, make sure you change it in the beginning. Okay, so I can follow you all the way through. Which side do y'all want to start on? Okay, left side. What would you do on the left side? Hey, I see an opportunity to multiply by the conjugate, don't you? 1 plus something, so let's multiply by the conjugate. That'd be 1 minus something. Is this the right way to go? I don't know. I don't know. Let's play out the denominator and see what happens. If I multiply through in the denominator, I get 1 minus cosecant squared of x. Okay, and then off to the side, if you're not sure what that's equal to, write the identity. We know 1 plus cotangent squared of x is cosecant squared of x. So what would 1 minus cosecant squared be equal? Not cotangent, but not cotangent squared. Not cotangent squared of x. It should be negative cotangent squared. Y'all see that? I got to bring the cosecant squared over here to get 1 minus, so I got to get the cotangent squared to the right hand. It would be negative cotangent squared of x. So that's what I would end up with in the bottom. Is that what I want to have in the bottom if you look at the right-hand side? No, there's a cotangent in the top. In fact, if you look at, I start with 2 cotangents in the top, and I want to keep one of them in the top. See that? So what do you want to do? Do you want to keep going down this route? Well, let's see. First of all, if I keep going on this route, do I want to distribute the cotangent up there? No, because typically we can divide out common factors, and if you look at the right side, it's factored. So I'm just going to leave this as 1 minus cosecant times cotangent squared. Let's not abandon it just yet. And then I got 1 minus cosecant of x times cotangent squared of x. The cotangent squareds look like they divide out, don't they? Crap. So now I'm left with 1 minus cosecant of x all over negative 1, which if I multiply that through in the top is cosecant of x minus 1. Okay, now here's the thing. I've kind of run out of things to do on the left-hand side. The only thing left to do really is to put it in terms of sine and cosine. So here is a legal maneuver. This is totally legal. Could I jump to the other side and do a little bit of work over there too? Yes, there's nothing wrong with working on both sides. Ideally you stay on one side because that's the preferred method. But there's nothing wrong with jumping to both sides as long as you keep both sides independent. Now, what would I do on the right-hand side? Is there any obvious math I could do? Well, even before I put it in terms of sine and cosine, I could distribute, right? Notice the left side is 2 separate terms now. And if on the right-hand side, if I were to distribute, I would put it in 2 separate terms. Yes, yes? Okay, so let's just see what that becomes. I get cotangent of x times secant of x minus, hey, what's cotangent times tangent? It's 1 because how are cotangent and tangent related? Reciprocals. Is that starting to look a little bit more like what we have on the left? Yes. Now, all we have left to prove is the following. Here's all that's left. I need to prove that cosecant of x is the same as cotangent times secant. The minus 1 looks like it's in place, doesn't it? Do you think I would accept on a test if you just put that as your next line and said your bottom lines are the same and you're done? I would not, because you did not show me how cotangent times secant, if it even is, how it's equal to cosecant. What did we learn last week if you want to know how 2 functions simplify down and they're not in terms of sine and cosine? Put it in terms of sine and cosine. This is cosine x over sine of x times secant of x, which is 1 over cosine of x. What happens with the cosines? They divide out. We're left with 1 over sine of x minus 1. And what's another name for 1 over sine of x? Cosecant of x. Now, do the bottom lines look the same? Yes, so now we're done. Yeah, 3 to the 100. So we got a couple strategies here, right? Change the variable if you don't like it. Change the variable if you don't like it. Just change it in the middle. Change it on both sides to start with. And then here's the next strategy. Work on both sides and meet in the middle, right? As long as you're working them as independent expressions, you can work a little bit on both sides. And what you've done here, notice you've created this logical loop of equivalent statements. You could jump in and you can go either direction. You can go from the right to the left, or you can go from the left to the right. Right? If you wanted to continue working on one side, you could just put all these little steps backwards on the left hand side, and you've got it. Okay. But notice it would require you to create something. If you have 1 over sine, you would have to know to multiply by cosine over cosine. So it's easier to just go to the right, distribute what's already there, and break it down than to have to build it up and know that you had to multiply by a cosine over cosine. Okay. Is that the only way to do that problem? No, not at all. Not at all. In fact, you probably could have called cotangent to begin with. You could have called it cosecant squared minus 1. You could have called cotangent squared cosecant squared minus 1, factored it into cosecant minus 1, cosecant plus 1, and then you could have divided out the 1 plus cosecant. Okay, so there's several different ways you could have done this. But y'all saw the opportunity to multiply by the conjugate over the conjugate in the beginning, and ultimately we stuck with it, and it worked. All right, comments or questions on this one? Any other kernels of wisdom we can extract from this one? What's that? It looks like a face? Okay. This would be the neck. And these are the eyebrows right here. Those are the eyebrows. Yep. I agree. It kind of looks like a face. And this is like a little goatee on the chin. It would need some ears, right? What could that be, the eyes? Yeah. These could be like sunglasses. There we go. And this is his hair. He's like Charlie Brown. He's got little squigs for hair. Yeah, I like. He has no mouth though, right? You know what that? You know whose face that looks like? That looks like Post Malone with all the graffiti on it, doesn't it? He got all those Trig tattoos all over his face. That's what it looks like. Post Malone. He should, right? If you want to be a popular artist, that's how you do it. Okay, next one. We're proving again. 1 plus cosine over 1 minus cosine, secant plus 1, secant minus 1. All right, step 1, draw the line down the middle. Now, is there a possible opportunity here to multiply by the conjugate over the conjugate? Yeah, there is. There's actually 4 opportunities to multiply by the conjugate over the conjugate, isn't there? I can multiply the left by 1 plus cosine over 1 plus cosine. That's the conjugate of the denominator. Or I can multiply the left by 1 minus cosine over 1 minus cosine. That's the conjugate of the numerator. Same thing on the right. I can multiply by secant x minus 1, secant x minus 1, or secant x plus 1, secant x plus 1. I've got 4 opportunities to multiply by the conjugate over the conjugate. Which one should we try? One of them is probably going to be a little bit smoother than the other in terms of getting to the right answer. Which one should we try? Should we try any of them? Is multiplying by the conjugate over the conjugate always the thing you should do just because you have the opportunity? If you have a hammer in your hand and you could swing it at someone's head, should you do it just because they're there and you're there with a hammer? No, don't swing a hammer at someone's head. Just because their head is there and the hammer's in your hand, you don't always have to do just because it's possible. So here's what I would do. I would hold off just because there's 4 different ways to do it and I don't have any insight as to which one would work. I could do trial and error and see what happens. But here's what I'm going to keenly notice. I'm going to notice that they're already very similar to each other, aren't they? They all have 1s in them, which is cool. So I'm going to notice the trig functions that I have. On the left, I have cosine. It's already a cosine. And on the right-hand side, I have secant. Now, the thing that jumps out to me is the fact that secant can be written easily in terms of cosine, yes? In fact, it's just the reciprocal, right? So my first step here would be to replace both of these secants with 1 over cosines. That gives me 1 over cosine plus 1 all over 1 over cosine minus 1. Now, in doing that, I've created a complex fraction, haven't I? And remember what we do when we create a complex fraction? We rejoice. We're happy because the next step is always to eradicate the complex fraction, always in the next step. Now, can we do state change flip here? We can't do state change flip because we have plus 1 minus 1. If it were just 1 over cosine divided by 1 over cosine, we could. But because it's plus 1 minus 1, we can't do state change flip. But you know what we can do? I already heard Peyton say it. We could do lick'em over lick'em. What is lick'em over lick'em? What is the LCM of your miniature denominators? Cosine. So I'm just going to multiply by cosine of x over cosine of x. Now what we're going to do is distribute. Remember, we did this earlier in the year. Our goal is to destroy the bunk beds upstairs and downstairs. Remember? We're destroying bunk beds upstairs and downstairs. If I distribute the cosine in the numerator, what's cosine times 1 over cosine? 1 plus cosine times 1 is cosine x. So there's your new numerator. In the bottom, if you distribute the cosine, 1 over cosine times cosine is 1, minus cosine times 1 is, compared to the left-hand side, how are we doing? Oh my God, we got it. Oh my God, we got it. So, is that the only way to do this problem? No, I guarantee if you multiplied by any of one of those conjugates and you kept at it, you would eventually get to the right answer. It would just be a much more scenic route. So part of what you're learning how to do here is you're learning how to use the tools that you're acquiring, okay? And not just using the same tool for every job. Okay, that's probably a better analogy than swinging a hammer at someone's head, right? You got a hammer and you got a saw. You don't really use a hammer to try to cut through a board, do you? There's a saw for that. And you don't use a saw to try and drive a nail. There's a hammer for that.
But I mean, the other one could do the job.
Right. If you're determined enough, you could probably cut through a board by using the claw end of the hammer.
It would just be a more scenic route.
It would be a more scenic route. You're right. Okay. Any questions on example 7? All right. Example 8. Prove the following identity. Boy, this is kind of getting to be the same. Same instructions. Prove, 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 prove. All right. Which side do y'all want to start on? The right side is not a bad candidate because, why, Brady? It's got multiplication and subtraction. So that means it has 3 trig functions instead of just the 2. It also has a higher power, remember. And sometimes it's easy to start with the higher power because you're tearing it down to low instead of trying to build something up to a higher power. Okay, so if we start on the right-hand side, well, they're already in terms of sine and cosine, so we can't really start by putting it in terms of sine and cosine. But what can we do here that maybe we did on the very first one that we looked at? I could distribute, okay? Let's see what happens if I distribute. I get sine squared of x times cosine of x minus sine to the 4th of x times cosine of x. Not illegal to distribute. I distribute it and I look at the left-hand side. How's that looking? Is that looking good? Not really. The left-hand side when we started was a single term. The right-hand side, really, it was also a single term, wasn't it? It was just that one of the terms had 2 terms in it. So we now distributed and turned it back into 2 terms. Dang it. So what are we trying to do here? Well, I still need to break down the power of sine to the 4th, and turn it into a sine squared. And at the same time, I need to build up the cosine from a first degree to a second degree. So I need to bring the sine down 2 degrees, and I need to bring the cosine up 2 degrees. Do we have a way to relate sine to cosine that is in terms of 2 degrees or squared? Rhymes with Papa Fid. Papa Pid. But I can't use Papa Pid yet. The only place I can use Papa Pid right now is I could replace that sine squared with 1 minus cosine squared. What could I do, though? I have 2 terms. Do we have anything in common? We have a sine squared that's common in both of them, right? And a cosine that's common in both of them. So even though we just distributed the cosine, do you want to factor it right back out? Yeah. Fine, let's do it. So I'm factoring out a sine squared of x and a cosine of x. Now, should we just go back and erase the first line and factor out a sine squared from the beginning? That's entirely up to you. We're like taking 1 step forward and now 2 steps backwards. Okay, you can just go back to the beginning and take 1 step backwards if you want. Okay, so I'm left with 1 minus sine squared. That's what I get when I factor out the sine squared cosine of x. And now OMG, now it's slapping us in the face. What's another name for 1 minus sine squared? That's cosine squared, isn't it? That's Papa Pid. 1 minus sine squared is cosine squared. And now what's cosine times cosine? Cosine cubed. Is that what we want? Yeah, we're done. Uppage. Unicorn pride is justified. Yeah. Unicorn pride is justified. So that works. That's a beautiful proof. Now, if you got rid of that second line, you could go straight to the third line. You could just factor out a sine squared from the very beginning and group the cosine together. It's up to you. But that's fine. We can call that a waggle. It's a little pre-swing, right? Multiply the cosine in, then factor it right back out. It gives you something to do. Gets the juices flowing. Anybody see another way to do that one? That's probably the best, most efficient way. So, what's our strategy there? Remember what our strategy was on number 1? Yeah, factoring. Look to factor, common factors. That's what that one was. That's exactly what we did on our very first one, except that we factored the first one as a difference of squares. But common factors work as well. That does look like Post Malone. We got to give him some teeth that are like grills. Yeah, yellow grills.
Did you know his face tats say always tired?
Always tired?
Yeah. From like both cheeks, always tired.
Is he always tired?
I think he is.
I mean, to have a message that you're trying to put out to the world, always tired.
Look, I looked it up.
Is it in Latin or something? Or is it in English?
No, it's just always tired.
Oh, it literally says always tired in English.
Yeah, he's got a hammer on his face.
He does have a hammer. Are you serious?
Being so serious.
I just talked about putting a hammer on someone's face. That's a coincidence.
Look, that first one, it'll be on that right cheek.
It's kind of blurry. It's not letting me zoom in.
Oh, yeah. He's got a face, a sword, a heart with 2 extra.
Oh, there it is.
X's, a Playboy bunny.
Oh, yeah, look at that.
It says stay away, always tired. A razor with
blood on it. I guess. Always tired. It does say always tired.
And he has barbed wire on his forehead.
I've seen that. That's probably the most noticeable thing. Always tired. Poor guy. Guy needs to drink some coffee or some energy drinks.
it dead?
He probably doesn't sleep. He's a dad? Oh, that's why he's always tired. The little one keeps him up. Hey, since he's a dad with a little one that always keeps him up, maybe his next tattoo will be dirty diapers. All right, let's look at the next one. We've got, I wonder if we can email him and say, hey, we have a suggestion for your next tattoo, dirty diapers. And he'd be like, if I'm awake, I'll get it done. But I'm always tired. All right.
I wonder if Cheyenne has
Cheyenne. All right, well, what side would y'all start on here? The right side or the left side? There's kind of conflicting information here. The right side definitely has more information, doesn't it? It has 3 terms times one term. But the left side has that denser nucleus, right? It has the higher power. If you have the higher power on the left, you have to know how to split it up. So I don't care which side you want to start on. Does anyone have any insight as to what to do on either side? Because there's really no wrong answer here. You would distribute. Well, yeah, here's the deal. I would not distribute. If you distributed this cosine, you're kind of polluting all that stuff there. In fact, here's what you want to do. You want to realize that you already have one factor of cosine available. You need to end up with 5 factors of cosine. So what we really need to prove here is we need to prove that this here is equal to cosine to the 4th of x. Does that make sense? That's what I need to prove. Okay, so I think I'm going to leave the cosine out and try and prove that. So how can I prove that that's equal to cosine to the 4th of x? Does it factor? 1 minus cosine squared? Yeah, but I'm just going to have to contend with that sine to the 4th somehow. The only way we can get the sine to the 4th to change into a cosine to the 4th is by going through the squared, don't we? What if I rewrote this like this? What if I rewrote this as sine to the 4th of x minus 2 sine squared of x plus 1? Should you recognize that as a factorable quadratic? You should. That's going to double bubble into something. What's the square root of sine to the 4th? Sine squared of x. So I'll have a sine squared of x in the first slot, a sine squared of x in the second slot. And you could already start foiling it out to see if it works, right? If you foiled it out, what is sine squared times sine squared? Sine to the 4th. Now, I'm looking for something that adds up to 1, so that has to be a 1. And these both have to be minus signs, don't they? Let's see if that works. The inside is minus sine squared. The outside is minus sine squared. That gives me minus 2 sine squared. That's good. And then the last would be negative 1 times negative 1. That's positive 1. So that works. All right, now I need to come off to the side and look at Papa Pid. I know that cosine squared of x minus sine squared of x equals 1. So what is sine squared of x minus 1 equal to? No, not cosine squared of x. I don't know. Why don't we do this? Why don't we solve this? This is plus right here. Why don't we solve this for, yeah, I'm sorry. I wrote the wrong identity down. So sine squared minus 1 should equal what? Negative cosine squared. Yeah, I wrote the minus sign down. I was trying to already solve it in my head. So this is equal to negative cosine squared times negative cosine squared times cosine of x. Now I think we got it. What's the negative times the negative? So I got cosine to the 4th of x, positive, times cosine of x, right? Negative times negative is positive. Cosine squared times cosine squared is cosine to the 4th. And now what's cosine to the 4th times cosine? Cosine to the 5th of x. Uppage. Factoring. You got to recognize factoring. Now, is that the only way to do it? No. Here's how you could have done it on the other side. You could split the atom, right? You could have said, all right, I'm going to call this cosine to the 4th of x times cosine of x. Why would I do that? I want to get one of my cosine of x's out on the side because that's what we need in our final answer. Yes, yes? So I pull one of them out, and that leaves cosine to the fourth. Now, here's your next step. This is the insight. You'd have to call cosine to the fourth cosine squared of x quantity squared. Is that the same thing? That's just writing it squared two different ways. One's in the condensed form, one's in the expanded form. Now I'm going to replace the cosine squared on the inside with something from Papa Pidland. Cosine squared is 1 minus sine squared, all of Papa Pid, yes? Yeah. Now, instead of having to factor, all I got to do is FOIL it out, or square and multiply double square. Square and multiply double square. Square the first, you get 1. Multiply and double, you get minus 2 sine squared. Square the last, you get plus sine to the fourth times cosine of x. Square, multiply, double square. And then you compare it to the right-hand side, and you're what? You're done. Uppage. Yeah, I'll do uppage every time. I like uppage. Unicorn pride is justified. That's my favorite saying. That's what we've been saying since I was in school here. And then it kind of got away, and now everyone has their own one, right? It's a great day to have a great day, or it's a great day to be a unicorn, or fear the horn. But I'm partial to unicorn pride is justified. Not only because it was the motto when I was a student here back in 88 to 92, but my father-in-law also came up with that slogan when he was president of the Sports Boosters Club. And I married his daughter later, and now he's passed away. So I try to keep Unicorn Pride is Justified alive. And if you don't think it is, say it enough times, like Mr. Kilford says, and you can fake it till you make it. You should be proud to be unicorns. I remember when we moved here from Austin, and I found out that the mascot was unicorns. I was like everybody else probably. I was like, I don't want to be a freaking unicorn. That's and I had a word for it back in the day. I said that's freaking. And I forgot what word I used, but it wasn't a nice word. Um, and then when I became a student, and I was like, you know what? We're not the fairy, fantasy, rainbow, mystical unicorns. We're the freaking fighting, mighty unicorns. We're tough. So then I started like, man, now I'm proud to be a unicorn, and it stuck. It didn't take long. 7th grade, baby, I was hooked on unicorns. Of course, they called us the Colts back then.
Yeah.
The Colts. Yeah. Yeah.
You know, the
And I was a member. I was a member in middle school of the CIA. Did y'all know that? I was a member in middle school of the CIA. Is that the Central Intelligence Agency? No, no. In middle school, the CIA, we got little cards that said official member of the CIA. And I felt like I was an important person in the government. But CIA meant Colts in action. That just meant we pledged not to do drugs or drink alcohol. But I was a member of Colts in action. Yeah, baby. That was like 1986. Woo! That was a long time ago. Little 12-year-old pledging not to do drugs or drink. I was a member of the CIA. I flashed my card. They're like, I'm a member of the CIA. Can I get backstage passes here? Nope, they're doing drugs and alcohol back there. I'm like, oh, that's not where I want to be. I'm Colts in action. Do they still call y'all Colts at the middle school? No, y'all are just unicorns. Yeah. See, there's no special name for a young unicorn. Colt just kind of means like a young horse. But it kind of, when you refer to yourself as a colt, it doesn't really imply that you have a horn, does it?
I think it could be that your horn hasn't come in yet.
Your horn hasn't come in yet. Maybe that's it. Yeah, maybe that's it. I never thought about that. All right, let's look at this last one for today. A baby unicorn is called Sparkles?
yeah, we're the Spartans.
Oh, that's freaking, insert a word for that. That's freaking awesome. I don't want to be a sparkle, and then you become a sparkle, and you're like, we're the fighting sparkles. We're the mighty fighting sparkles.
Could you square both sides?
No, you are not allowed to square both sides. You can't do something to both sides of the equation. You can't add 5 to both. You got to work each side independently. Independently. Okay?
Like the right, the side, the other side.
What would you do? What side would you start on?
The left side.
The left side makes sense here. It's factored, and you got 2 terms times 2 terms. The right side is 2 terms. So you could distribute right away, couldn't you? Like you could FOIL this thing out. If you FOILed it out, you're expanding it and making several terms. So that's what I would do. We get sine of x times tangent of x. Start on the left-hand side. And then we get plus sine of x times cotangent of x plus cosine of x times tangent of x plus cosine of x times cotangent of x. And now you're like, freaking yeah! The left side has 4 terms and the right side has 2. So I got some more work to do. I got to get rid of 2 of the terms and I got to get rid of all the sine and cosine. Now, we've already seen this today. I've got 4 terms and I don't know how they simplify. In order to see if and how something simplifies, we should do what? Put it in terms of sine and cosine. So you could have done that as your first step. I think I heard Brady mention that. But I'm going to do it on the next step. So that becomes sine of x over 1 times tangent, which is sine x over cosine of x, plus sine of x over 1 times cotangent x, which is cosine x over sine of x, plus cosine of x over 1 times sine x over cosine x, plus cosine of x over 1 times cosine x over sine of x. Now, as you go through, let's take inventory. In the first one, nothing divides out, but I do get sine squared of x over cosine of x. Yes, yes? I multiply straight across. Look what happens in the next one. The sines do divide out, and I'm just left with cosine of x. Plus, on the next one, the cosines divide out, and I'm just left with sine of x. And on the last one, I get cosine squared of x over sine of x. Ugh, did that help me? No, but here's what I do know now. I know that everything on the left is in terms of sine and cosine. If I'm trying to match it up to the right-hand side now, would this be a good time to jump to the right-hand side and put it in terms of sine and cosine? So I can start comparing apples to apples? Yeah, I would. This is where I would jump to the other side. Secant is 1 over cosine, plus cosecant is 1 over sine. Oh boy. Any help would be nice. I could do pop-up hit on the top part if they had the same denominator, right? I could do sine squared plus cosine squared if I can combine them over the same denominator. They have different denominators, don't they? So I can't just say it's sine squared plus cosine squared over both of those. So I can't use pop-up hit, but I do see them there. I could turn sine squared into 1 minus cosine squared. You want to do that? Let's try that. I mean, what the heck? I'm kind of stuck. Let's do sine squared as 1 minus cosine squared, and that's all over cosine. And then plus cosine, plus sine. You want to do the same thing on the end and turn cosine squared into 1 minus sine squared? 1 minus sine squared, all over sine of x. Okay, great. That felt good. Now what? Now look what happens. I can split up the numerators. Remember I told you that was a strategy too? I can split up the numerators by putting them each over the denominator. That gives me 1 over cosine of x minus cosine squared of x over cosine of x plus cosine of x plus sine of x. Splitting this one up, I get plus 1 over sine of x minus sine squared of x over x. Now, that's a step in the right direction, isn't it? Because look, what do I want on the other side? I want a 1 over cosine of x. Do I have a 1 over cosine x term now? Yeah, and I want a 1 over sine of x term, which I have a 1 over sine of x term. So now I'm hoping that everything else that's listed there goes away, right? Go away, everybody. Boo, go home. Boo, get out of here. Well, let's see what happens.
That's beautiful.
Do you already see it, Ryan?
Yeah, you can cross out all the
Yeah, what's cosine squared over cosine? It's just cosine plus the cosine that's there. And then I get plus sine of x, and then I get plus 1 over sine of x. And then sine squared, oops, this is sine squared, this should be over sine of x. This becomes minus sine of x. And now you can show me that the cosines cancel and the sines cancel, and now I'm just left with 1 over cosine of x plus 1 over sine of x. And is it written in the correct order, or should I put the sine of x first? No, that's the correct order. So I finished, right? Uppage. There you go. So you just fiddle around with it. You keep going until you run out of things to do, then jump to the other side and do as much as you can. That was what?
That's a lot, right?
But writing's easy, right? We're not afraid of writing. There was a lot of like just rewriting things, but yeah, it's okay. All right, so we'll finish tomorrow with a Kodiak grizzly bear. Y'all know what a Kodiak grizzly bear is? They're the biggest, fiercest, meanest grizzly bears on the planet. They live on Kodiak Island, Alaska, where the food source is plentiful and the predators are few.
They make good pancakes.
They make great pancakes. I don't know what that means.
You know Kodiak cakes?
No.
They're like protein pancakes.
Oh, I see.